All right, so 3D structure of DNA, okay? Two single-stranded DNA chains are going to come together and form a double helical structure, which is, we got a couple different renderings of how that might look from your textbook. So there are some essential features to think about with the structure of DNA. So one, the strands are going to orient themselves in opposite directions, okay? The 5' end and the 3' end of the other one are near each other, and vice versa. Yeah, 5' to 3', and 5' to 3' goes the other way on the second chain. Essential feature number 2, bases are on the inside, and the sugar phosphate backbone is on the outside. So, what was the answers that we came up with for that last question that said, which of those 3 pieces was driving this inside-outside piece? The sugar, okay, who agrees? A couple hands. Who thinks it's the bases? More hands. Who thinks it's the phosphate? I'm just kidding. Alex is awesome. It is the phosphate. Phosphate's the driver. Phosphate has the charge on it. It has the most power here because it has the charge on it. You don't have to change your answer. Unless you want. We can talk about it again next time, but where are we? Here we go. So the charges want to get away from each other. So they go to the outside. The charges also want to interact with water. They're fine with that. The bases, not really interested in interacting with water. Sugars, not so much. They'd rather interact with each other. They go to the inside, phosphates go to the outside. Phosphate is the driving force for that shape. Okay. Hydrogen bonds form between, this is essential feature number 3, the H bonds are forming between a purine on one strand and a pyrimidine on the other strand. Okay? And that pairing is always exclusive. Okay? It's A to T and G to C. Any questions about this stuff? It's familiar stuff for the most part. Oh, I love how I put a question here for you guys. What is the other bond we learned that's missing from this picture? Bonds that it give us. Hydrogen bonds in between our bases. Glycosidic bond, this is the bond that is formed between the sugar and the base. We didn't put a name to that earlier. Go ahead and be comfortable with that terminology. We said that the base attaches at the C1 spot, but we wouldn't put a name on that type of bond. There was one more bond we learned, then the label here, which was phosphodiester. Beautiful. So this was that seminal paper that Watson and Crick published in 1953. This is the whole thing. One page where they describe the structure of DNA in all its glory. Okay? The original publication that said, here is our proposed shape for the DNA structure, the double helical structure, which maybe it's more of like a story, but I feel like I've heard that they literally just like cut out paper and fit it together like a puzzle until it made sense. I think that's true. They also said this statement in their paper, it's like this one of the very last lines here before it gets into like acknowledgments. It has not escaped our notice that the specific pairing we have postulated immediately suggests a possible copying mechanism for genetic material. So at this time, the concept of replication of DNA, transcription to RNA, translation to protein, that didn't exist yet. They hadn't come up with that. They knew DNA had the genetic information. They just didn't really understand what that meant, how the copying would work. They pretty much were already figuring it out with structure alone at this point. Here's another maybe pretty picture of the pairing of adenine to thymine and cytosine to guanine. What is the primary difference between these two? Number of hydrogen bonds. Hint, 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 hint. There are 2 on the top, there are 3 on the bottom. Why does DNA and not RNA store the genetic info? Who wants to put a guess to it?
Is that RNA has the OH group, so it's more reactive?
Perfect. That is a beautiful answer. The short answer I gave was chemical stability. But the reason that it is less chemically stable, RNA, is because of that OH group. By having that oxygen there, it is more reactive. It can interact with more stuff, it can just cause more problems. And one of the things that it can do is it can attack itself, okay? So here we have our chain, our long chain in the 5' to 3' direction, okay? And normally on our deoxyribose in our DNA, there's no OH here, this is just an H. But on RNA, the O is present, and that O can come in and interact with the phosphate group and basically self-cleave itself. That's one thing it could do, but it can also start interacting with other stuff. It's just a site for more interactions that just essentially it is less stable.